Hey, it worked.
It's because you have me.
Yep, extra luck. All right. If memory serves, we were here last time. So I believe we had gotten up to this point. All right. So what we want to talk here, there's actually a whole bunch of different weightings that are out there. The most commonly known weightings that are out there have to do with how do I measure the two major time constants, T1 and T2, and how I do a proton density weighting. So again, the idea of each of these, I added an extra slide, that's why I have to re-download them. That gives a better image of why this is the case. But if you think for a second, right, T1 weighting is basically comes from the fact we get really highly excited on the T1, we let the T2 stuff wait out, and then we give it a kick. And then whatever's on T1, right, the Z direction, now comes down onto your XZ or XY plane. And that's going to be what we'll watch then decay, and we'll put the echoes in. So in essence, we usually we excite it, and then we'll, the T2 stuff goes away, there's a little bit left, it comes, the T1 hasn't fully recharged, we kick it back down. Now it's all just T1 stuff, watch it decay and measure. That's basically what it is. So for the echo time on that, right, it's already had a loss, so we want that to be fairly short. We also want the TR to be short because we're kicking it over, and I'll show you where. We want a decent contrast between these. If we wait too long, we lose all our contrast difference on that second kick down. Nobody here is showing the two kicks because it's the only one that takes two kicks. You just have to remember it. This one takes two kicks. But it's got to be short on those. And the main reason, in essence, our recovery time is going to cover this one when it comes in. When we come down to T2 weighting, everything is going to now be governed by TE. All right? And so we'll need TR to be really disgustingly long because we just want everything to go back flat and start it all over again. Remember this one, I don't want to start it all over. I need that kind of double shot. This one I need clear between everything. I need a fairly long TE because I have to get a contrast set up. And I'll show you why that works. And that's, you'll notice on here when it gives you, this is the books table. They only give you that little tiny area with the notes. They'll tell you that they want, TE to be approximately equal to T2. That's the weight. So remember, the weight on this one's going to be E to the, and you've got your time constant divided by TE as essence. It's technically over T2, but if you set TE equal to T2, the 63% decay spot, you'll get a good contrast. So that's why they make that comment of TE equal T2, and you just set TR long enough that it's well out of the zone. With the T1 again, our big concern had to do with TR. We had to make sure we were setting that one for the contrast. So that has to be short. So that has to be really short because TE is always shorter, or almost always. Right? This is the only one that's a little bit odd. And to understand this one, it's actually kind of a mixture of these two. We basically want to kill both the T1 and the T2 signals because the proton density signal is weaker than either of the other two. So we've got to make both of those other ones go away. Right? And we do that by making TR really, really crazy long, which basically kills off your T1. And we set the TE really, really short, which makes T2 stick. And I'll show you in a second why that is. But this is where this one comes from. Basically, you're trying to damage both of them, and once both of those are basically gone, the only thing left is PD. So that's kind of the idea behind them. Let me show you why you pick them. The best way I know, and I actually found somebody who drew a little picture of this, so I was happy about that. Imagine these are your decay curves. Right here I'm plotting, this is a material with a really short T1, i.e. your T1 dams away very, very quickly. So it's gonna come out very fast. This one is one with T1 is really long, so it takes longer. By the time you're up to about 2,000 milliseconds, about 2 seconds, pretty much everybody's damped out. Right? So this is fast decaying materials, slow decaying materials within your body. So this is the range. So between those curves, that's the contrast you can get on your image. So if you're over here, you have almost no contrast. If you're up here, you have almost no contrast. So you have to find a spot in between on there. So for a typical material, this is going to happen if you set this right about 2/3, about 67% of the way up, you'll hit most of the materials. Right? At that zone, you're pretty darn close to the whole 1/E. Hence why they say, roughly speaking, set TR equal to your T1, because that'll get you to 1/E, which is pretty darn close to the maximum peak. So that's the whole reason this came in. So this one tells me TR is therefore what I want. If you look at your time scale, this is like 300s there and 600s there. So somewhere between 3 to 600, that's the range you want TR. That's really, really short, right? Because you don't want the T1 signal gone. All the other ones want the T1 signal gone. That's why they make TR so far or so big. So a short TR means you still want that T1 signal existing. Okay. So does that make sense why that's picked? I think that graph is probably one of the most useful ones in my opinion for making that real. Let's cover this one. And then the mid one is going to be, I'll show you where it fits. It's again from those two. But you can again see right at T1, it makes total sense, right? Read out however you want to do it, either by FID or by an echo. If you're doing an echo, it's going to be short. But what you really care is TR equals T1. Right? Setting that TR to be right about the spot where you're at the time constant for the system for T1. Right? For T2, now the echo is what matters. So now we're taking a look at T2 decay. This is right after it's been kicked and it's decaying away. Right? Materials with a long T2, materials with a short T2. If you wait too long with the short ones, they're gone. Right? If it's really, really short, nothing has happened much. So you now have to pick this so you get a good distance between the curves. Again, we're on a somewhat similar area, so now we're picking TE, right? We need it to be a little bit longer so there's a separation between the two. So again, this is probably somewhere ballpark range, 100 to 150 milliseconds for TE. That is really big compared to this. But again, remember, in this one, we had a much weaker signal because we weren't dealing with the full T2. We were doing with a T1 that decayed and then kicked into T2. Right? So it's kind of twice decayed. It wasn't a very strong thing. We needed it quick. And on this one, I'm trying to get them to spread because I want the T2 dynamics to be what matters, not the T2 dynamics don't matter much at all. I really care about what energy came into it. So we set that about 100 to 150 milliseconds. This has to be way bigger so it doesn't interfere. So we set it out 2 to 6 seconds between them. That's long enough any effects have died and are isolated. Does that make sense? All right. Now for PD, I want both of them gone. All right. So if I set TR big, all right, over 2 seconds, 2 to 5 seconds, 2 to 6 seconds, somewhere in that zone. That means that all the T1 stuff is gone, right? I set TE really small, 10 to 20, right? Similar to what's there. There hasn't enough time, right? So with the 2000 plus, the materials don't really matter that much. There's no contrast for T1. With TE really small, this is the one that cares about TE, we're down in this zone. Again, there's not much contrast at all between them. So essentially, I've removed the contrast of both T1 and T2. So those signals are there, but there's really no difference in them. So it's kind of like a constant gray that we're adding on no matter what the material is. So there's really not much of an effect. So the only thing that's left, and remember, the T1 and T2 signals are much stronger than protons, right? So we've got to make sure those ones have no contrast. And all this does, when there is no contrast, it requires a difference between the curves. If I'm over here, no difference. If I'm out here, no difference. T1 and T2 don't matter. Right? They're there, just a constant, and a constant can be ignored. With the protons, right, that's the only thing left causing any variation. The more protons you have, the stronger your signal. That's the proton weighting. So things without a lot of protons in it will be weak. Those with a lot of protons will be strong. Yeah.
So I'm a little confused why we need a kick to measure proton density if we're not measuring T1 or T2 contrast.
Because you still want, you don't want it to correlate to either of those times.
Okay.
But you still need a signal. If you don't kick them at all, they're completely random, so they all cancel and you get nothing. So you have to have some correlation, you just don't want them decaying.
Okay.
You want the only thing that matters is that there's just sheer different amounts of them.
Okay.
Right? So by setting TE really small, they haven't had a chance to dephase yet. I'm just going to take a sample right then. Okay? And then how strong your signal will depend on how many signalers you have, because they're all pointing in the same direction anyway. Does that make sense? Awesome. So that right there, in a nutshell, is the basic ones. Now, there are all kinds of other fancier ones that go on. The question of why we care about them, the fun thing between these two, right, T1 and T2, has to do with how fluid responds to them. So if you're wondering why do they do it, T2 tends to give a better signal strength to fluids than T1 does. Right? So in general, since most problems in the tissue are associated with fluid buildup, because if you've got some type of a your system's out of line, whether it's cancer or whatever else, you tend to cause fluid buildup in those tissues. If you've got edema or whatever else, fluid buildup, right? So generally bad stuff happens with is associated with extra fluid building up, even though it's not necessarily the fluid buildup that causes it, but it correlates highly with it, right? So it tends to make T2 brighter when you get more fluid and T1 darker when you have more fluid. So that's what you're looking for, is tissues with those artificial perturbations. That's one way you can kind of tell the difference between them. PD is really good at telling the difference between white and gray matter. The big advantage, so you can also tell it in T2, but T2 has more trouble distinguishing with the really, strong showings of fluids. So if you're looking for a tumor that's going on in one of these tissue areas, it can get hidden by the fluids. So PD is often useful for those type of situations. There's a whole bunch of other ones. I don't want to make this a medical class per se, but I do think it's helpful to know about them. And that's what we're trying to do, why we're trying to get each of these, right? There are much more complicated sequences out there, like I said, to really refine it. Yeah, sure.
This is just going to be a practical question. For a given imaging system, if you're imaging one patient in one sitting, do you normally take scans of each type, each mode?
No, it's going to be depending on what the doctor wants.
Okay.
So let's say, for instance, the doctor says, I'm suspecting that there's going to be, some type of an edema under the skin, whatever else. And so from that, they're going to select what they're interested in. Okay, I really care about a fluid differential on my T2. Okay, that's right? I'm looking for a tumor in the white matter of somebody's brain. I want a PD for it. Because, so you look at, for a doctor and working with a radiologist who would be an expert on MRI stuff, they'll say kind of what are they suspecting, what are the problems. If you don't know and you're just doing a blind search, they might do a couple of these different things. But that's going to be a really long, expensive test. So in general, you have some suspicions, and so you aim them towards the suspicions. Yeah. All right, so let's start talking about some of the pulses in a little more detail. So this is probably the simplest sequence you can imagine coming up. This is kind of your simple FID reading, things of that sort. That's coming on. There's no echo, anything of that sort that's happening. So remember these ones that we have here, slice and frequency at the moment, that's going to be basically encoding your spatial location that's going on. So this will set my slice area, and I turn it on at the same time I give my RF kick. And that means only the ones that are resonant with my adjustment of my frequency, which I do by the height. Right? So I set the Lamore frequency by how much I'm changing it with my Z gradient. And then I pick the RF kick to have the same exact frequency to that. So that slice and that slice only will resonate with it. So that one's now resonating. And then, after a little bit, I'm going to be able to measure, right? So I'm doing some stuff I can't measure here because I got to cancel all my little phase corrections and everything, right? So, because this is, if I was trying to, I don't want this to go on forever. So I have to kill that off, right? That will allow this signal to become apparent and visible to me, right? At which point, once I hit the peak, I want to turn on my frequency encoding, my X direction. And that's going to allow me to read out the X because it will change the frequency slightly along the X gradient. You'll measure it all at once, but the frequency spread will allow FFT to separate it out. So I'm sampling on my analog to digital converter at the exact same time I'm doing the frequency encoding. And basically, if I look at what that does in terms of, this is kind of my K-space plane, notice that causes this to happen. In essence, I move from the origin in K-space straight down the U-axis. This is kind of my X direction, that's my Y. Notice I didn't give any Y perturbation. Since I gave no Y perturbation, you stayed at the origin. So it literally, that's why this is such a simple one. If you're wondering, why was there no Y perturbation? Because I was measuring the Y equals 0. That's why it's a simple one. It doesn't involve any adjustment or encoding on that. It literally just reads straight down. Okay? And so all I'm doing with this. Now, notice I also start at the origin. If I wanted to read the entire thing, I would have had to push it back and then write down. All right? So I'm really just reading this portion of it. So, that's going to be, whatever is my sample time, that's how I pick them. All right? So I've got, that's how long to encode it. I need exactly that amount of time again when I'm getting rid of it, correcting it so I can get my signal back. That's why I read those, and I just leave literally that sample time. All right? I can add a little bit of delay time to clean it up, or I do some signal to realign everybody in the way I go. Next measure.
So on the very top of the RF portion of the graph, it shows just one pulse. Does that represent like a group of pulses to get a certain contrast? Or is that
No,
just
that's one pulse.
Okay.
Yeah, and they're showing the envelope. So there's a signal inside that envelope that's really fast. But that's a basic envelope because, what does that envelope look like?
Rectangle.
Yeah, this is your sync. So sync to rect. It's truncated, right, and corrected for the truncation. So it's not going to be perfect for rect. You're going to get the overshoots and whatever. Right? But it will be reasonable, right? At least somewhat close to it. So we're trying to give a nice uniform push.
Okay, so if we are doing an imaging mode, say T1, T2, or TD, if we needed to give it multiple kicks after a TR?
Yeah, so this one, and we'll take a look at them. This is the simplest one. This is your 90-degree kick.
I see.
This is what just happens if I kick it and measure it. If you kick it and measure it, you walk down that axis of K-space or Fourier space, right? Because it really is just Fourier space.
Okay.
So we're about to go through on the succeeding slides. We'll show you how to measure in all kinds of other directions. Good? Awesome. So now we're going to want to measure some angle. How do I get that? So again, this is a single line starting from the origin. You're moving in X and Y. So if you just think for a sec, that means I've got to be pushing X and Y. I've got to uniformly perturb those so they start spreading out. So it's just a tilted plane. Which you'll notice, again, this is my Z gradient. Pick your RF pulse to resonate with it. Turns on one slice of my body. Wherever you pick it, again, from the height of this, up or down. Right? Again, your correction, that sets up your TP time to when you can measure. I'm not doing anything fancy with the measures, so I'm just reading out. But I want to read out along an angle theta. And I set that theta so that GX and GY, GX, GY. All right, so you can measure that angle basically by the ATAN of those two. All right? So I just set X and Y, and I leave them both uniform for the reading. By doing that, I am now walking along that axis. So therefore, the conversion into Fourier or K-space domain is going to be along the same angle. I remember what we did with X-rays. Right? This is basically the radon transform, right? Whatever line you're walking on, central slice, that's the same slice you're measuring in the frequency domain. So nicely it walks along those same. So all I have to do is do the perturbation. The ratio of these two heights will determine that angle theta. When this was 0, it was just straight down here because it's GX and no GY.
So when you say walking along that vector in K-space?
Quote unquote.
Right.
Yeah, yes.
So
You're getting all the frequencies at the same time,
I see.
right? So in the frequency thing, you're getting that whole measure because they're superimposed. In the spatial is being perturbed down it, and I'm calling that walking it because the side at the lower side will be rotating at a lower frequency, the slower, and the ones at the highest gradient will be, the lower frequency will be slightly higher.
Okay, so just so I can think about this correctly, so the TS length, is that going to determine your sample frequency in your K-space?
It'll determine how far out you go. Yeah.
Okay.
Which, since that gives you a distance, in essence,
Right.
in that frequency area, it does, because remember, the further you are in the frequency, right, the bigger that region you go, that's determined by your sampling time.
Okay.
So there really is, amazingly, sample time does relate to your frequency domain, and they are inverse.
Okay, so when you say they're inverses, does a longer sample time give you a larger sample in K-space?
It gives you a larger distance between the useful data points you're getting out.
Okay, that makes sense. So then, during the sample
So you
period.
if you give me a longer time, I'm getting a better density on them.
Right, okay, that makes sense. That's kind of the relationship I would expect. And then when you actually take your ADC samples in the sample time, that gives you the length of that. Is that correct?
Yeah, because in essence, you're getting a whole bunch of measures here,
Right.
and you're gonna have to do a Fourier transform to resolve out the frequencies.
Right, okay. I was just making sure that it behaved
Absolutely.
the way I
It
was.
really is exactly what you think it's gonna be.
Okay.
You know, but that's how it's designed. We made up a sequence of events that are caused to encode frequencies. And we're just corresponding the frequencies to space.
Right.
So you can decode them later on. It has a meaning to us. All right. So let's step it up. All right. What if I wanted to read the whole line? That means I have to push myself back to the extent of where I can do measurement and then read the whole thing. That's why this is going to be half of that. All right. So again, kick, resonance, wait till it's ready. Now, I put this one in the negative direction of whatever it is, and it basically excites everybody backwards, right? This one is in the X, so it's going to move me backwards in the X. Right? Now at the end of this, I've got all of them with that slight perturbation going the other way. So they're back here frequency-wise because I've reversed them. Right? If I was originally fast here and slow here to read down, now I'm reversed. I'm fast slow instead of slow fast. So when I now impose this, it's going to reverse the directions and they'll start spinning up, and therefore I'm starting from the negative side and going all the way down. So again, we're on here, so we've ignored Y. But this allows, by doing the initial first pulse here, it allows me to kick all the way to the negative direction. Because if I were to read here, I'd be reading along that line. I'm just not doing the ABC readout there. Because what do I need? When this is done, I'm here at whatever extent I could have made out. And then I read for TS. So now I read down this whole line. Again, you can imagine this should be a longer TS because I've got a bigger space I'm covering. So if you're sampling inside there, like this is the time I'm sampling, but it's not the sampling measurements between each measure, right? That's the time period over which, right, I'm doing a discrete time on. So therefore away it goes, right? So it's that exact same idea though. Nicely, I can just kick them in opposite directions. And these are just, remember, the square ones are gradient magnets. How do they adjust my speed? So just spin them a little bit the opposite and then let them flip back. And that's just going to be little adjustments of their frequency speed. Okay, does this make sense? Let's step it up a little bit. Let's say I want to read off the axis. So now I need to have a shift to get to a perturbed space. But that shift here is in the Y direction. So therefore, after I do all my kick and I'm ready to go, I'm going to need a short period of time, and the height of this will depend on how far you move. Right? The positive shifts me this way. If I had A below, it would shift me down. So I can now shift up, and then I do my shift over in X and read them. By convention, we do the shifts on Y for the phasing, dephasing, and then we do the readouts along B. Right? You don't want to shift these because when you're reading your points, you're literally just kind of recording them into the matrix, writing the values down as your Fourier transform. So if you sometimes read this way and sometimes that way and whatever, you're going to get garbage. Does that make sense? Okay. So you can now see for this one where it shifts. And again, this is just going to be your kick for up. All right, so we have this second time period we have to do to get me into my shifted baseline to be able to read them out. Okay. So what if I want to read that whole line? See how we just build them up? Now, if you were to look at one of these later charts, I would submit to you it would be very hard to read and understand. So this is why I like walking through those slowly. So again, we kick. Yay, that's the usual stuff. I now want to be able to get spatially off axis. So I want to read some height, right? So the slice will determine here, y direction here, right? How far out or back from my center line. That's determined by this, right? Because I'm setting that dephasing on them. It shifts me up in direction. I want to read the whole line, not just half a line. So I have to initially, in the x direction, kick it back. That's the movement of B. So I set the x gradient coordinate. Remember, this and this, half of it have to be equal because I'm trying to read symmetrically about the axis. This is going to be how much time you basically got with that, with the number of samples that are going on. It is going to determine your resolution and frequency range that's happening there. Making them equal gives me a symmetric measure. So while I'm doing the reading, I've got to be the constant drive on this. So if this is my sample one, this has to be sample over 2, and this basically has to be enough to perturb them for the phase dephase amount that you need to do to set those off-axis plane. And then yay, I'm done. Right? Now I can read an off-axis. By adjusting this and its height, I can now read whatever stupid line I want. And I can start filling in my K, my space, my phase space that's on here. Right? Okay. Spin echo imaging. So it gets, all the ones we've done here, we were directly measuring fit. It gets a little weird when we want to do echoes. Because remember how we had to do an echo? We had to do a 180-degree kick. When you do a 180 kick, what is a 180 kick going to do in frequency space? It's a phase shift of 180, which is flipping the graph. So this right here is the result of you doing that echo kick. It's going to take you wherever you had set yourself up to be. It's going to do the 180. So you have to think, where do I want to do the readout? And you go, oh, I want to start here. I know I'm going to do an echo, which means I have to have a 180 kick in. So it's going to flip me. So then you have to set yourself up for the kick so that when the kick is done, you're ready to go. So you kind of have to think backwards when you're working on it. If there was no echo and you could just directly read FID, you would only have to do the upper part of this. So this is almost kind of like backing a trailer up versus driving a car. Right? When you're backing a trailer up, you have to kind of do some reverse because the other end is going to drive a little different. So if we were just doing a FID measurement and I wanted the bottom, I just perturb down, perturb over, read out. That's why if you can do FID measurements, do a FID measurement. It's simpler, it's faster, everything else. Echo gives you a much stronger signal, but now you have to do something a little bit. Does that make sense? Okay, so then let's think it through. This again, slice selection, impulse, right? That selects our slice because of the resonance frequency. Once that is done, right? Now I'm kind of here is my FID stuff. that's starting, and I would be measuring FID, but I can't measure FID. It's not doing what I want. I need an echo pulse. So this is no good, so I'm not going to measure that. But that is what's happening. So instead of taking advantage of this, I'm now going to position myself so I can do my echo measurement. I perturb Y in the opposite direction I want to go. So it goes up because I want to go down. And then I perturb X, so I am now in the complete 180 opposite through the center. I need that mirror through the center symmetry. It is now set up, right, at this point, so you can now do your 180 kick. Why that?
Oh, why there's Z? Because we need to excite the slice again.
Okay, so the RF pulse is because I need to flip it, right, to cause the echo. Right? And notice that the 180 is exactly here. So I need that 180 pulse to get this echo to appear. All right, so that's why the 180. Why the Z?
Well, you need to just hit the same slice again.
I only want to hit that slice. If you do this and you don't put the 180, you'll be kicking every slice 180. So that means all those other ones are going to get some energy. When they get some energy, they're going to generate some signal. By putting in the Z gradient coil turned on when it's happening, it will only do it in the resonant ones. So now you can selectively kick the slice. You're trying to keep noise, right? All those other slices are noise. If you accidentally kick them with a 180, remember how strong, the bigger the angle you kick something through, right? And realize kick is just a colloquialism, but I think it's a useful colloquialism. The stronger you are hitting it, it's proportional to the angle, right? You get a stronger signal the bigger that angle is. Can I get a bigger angle than 180? Now that's as big as I'm gonna actually perturb the system in here. So if I don't do this, yeah, I'll get an echo in mind, but I'll also get a really strong signal in all the others, and everything's going to be noised out. And you will get no good measurements. So that's why whenever I'm doing that RF coil, I've got to sync it up with my Z. RF and Z must act in tandem. Otherwise, you excite lots of slices and you get a noisy signal. It's useless. Right? In general, unless you're reading on diagonal, and you're almost never reading on a diagonal, you're only going to have your readout, the ABC, analog to digital converter. You're only going to be doing your sampling with your X encoding. Right? Why not do all my encoding and then read out? I need something because otherwise they'll start removing that shift of frequency. They'll go back to normal. So I'll lose that encoding on it. I've already done dephasing. This will just confuse the dephasing. Right? It'll build up the dephase so that now it's a tilted plane rather than a normal one. That's not what I want. Okay? So, I have to read it out. In my convention, we only read out on X, so that we're only reading out on X in my case space. Again, there are sometimes you could potentially do a radio readout, but that's a really specialized space. So for standard ones, that's not a thing. Okay, so now I've got my kick, I'm down here, now I flip, so all I have to do is in essence, get ready and read it out. So I do nothing for whatever it is that'll make the echo time, right? So from here to here has to be the same as here to here. So every time all this stuff has to be reproduced here in the weight. And then I read out with the encoding. And this just, again, sets the Moore frequency in left to right direction to be slightly different so that I read out an entire line in one time. Yay. And I bore my poor daughter. Yes.
I have a question about timing. So we talked a little bit, are we gonna talk more about timing?
It's ask whatever question there is, because
So-
there's no guarantee.
Okay, so when we take, this slide is one measurement of one line in one slices K-space. So are we gonna have to take
Yeah.
a bunch of lines and that's just
Uh-huh.
one slice and then we move slices and then do it again?
Uh-huh.
So is that gonna
So can you imagine how long this takes? Each of these things takes a few seconds, right? If you remember our timing, these could take anywhere from half a second to 6 seconds
Right.
per measurement. So if you remember from that, depending on whether we're reading, T1, then it'll be faster, right? If you're doing T2, it's gonna be really slow. NPD is kind of somewhere in between here, but closer to T2's timing. So depending on what you're reading, let's take a worst case scenario. I got 6 seconds on a really slow readout of a T2. You are now at that point, you've got 6 seconds times every one of those reads. You got maybe 500 lines, 500 slices, right?
We can take like all day.
Well, I mean, you're still talking 6 seconds here in the worst case scenario, right? So you're gonna do a slice in a few minutes. And then however many slices through your body. So you can now see why usually you'll try to do, say, like a millimeter or less resolution inside a slice. Because that just determines, right, this TS time, which is not your biggest weight. So I can get a higher resolution slice without adding, it adds some time, but it doesn't add a lot of time. I need faster readout equipment and a little more time, and I can get a better frequency map for you. Therefore, I can get better resolution in X and Y. No problems there. So how do I make up my time? I do a slice every approximately 2.5 spacings of what you're gonna do in plane. So if I'm 1 millimeter, I'm gonna be 2.5 millimeters between slices. So I take less slices to end up in a reasonable time here. And then aligning whatever the slice is to what you care about becomes kind of important.
So can you just take a thicker slice if you want to take fewer slices? Or is that?
Yeah. So think about what the thicker slice has to do, right? I need a bigger area where it'll be resonant.
So your sink just needs to be.
Right, so it's gonna depend on how tightly I couple those two between my Z gradients, that will determine, right, what it is. The stronger your Z, you've got more little slice areas where the resonance will be small. If you set that Z down, right, the same resonant frequency range is now across a bigger one. So when you want thicker slices, you use less Z gradient. That's really kind of the trick of it. And so now you can take a thicker slice. But again, that's why, I mean, it seems weird to say, Z gradient will determine your slice thickness. Does not intuitively seem to make sense until you think about, oh, that's setting the Lamore frequency. If I do less Z gradient, all that's gonna do is just all the way down the line, it's a shallower slope, so a bigger part resonates. It's a good question. Any other questions? Awesome.
And how many, about how many slices, if
512 by 512 is fairly typical resolution. And then slices maybe 30. Which if you think about it, right, just consider powers of 2 and everything, right? So 30 is we're going close to 32, right? So you're at that point within a nice reasonable factor of it. It depends again on how much you want. You can go up to 64. How much resolution do you really need? If you're in the brain, it's probably higher. If you're in the chest, it's going to be lower. So this all depends on the doctor's needs. All right, So here's another one of these lovely little trajectories. They're including on here something we didn't include on the last one, which is cleanup after. I remember we just kind of ended. So we're going back to a simpler sequence, no flipping here. We do one motion over. So you'll see on this, we've got my slice selection, that's pretty typical. Notice I've got my X and my Y acting simultaneously. X is down. The Y one here is shown as kind of a range because that's just going to determine which one do you go to. X down means push over to this end. The Y is shown as a range here because did you want to go up, down? What do you want? In this case, I'm going down. So I'm most of the way down, so I'm probably like this one, right? So I've got that as my kick. And generally, I want to do this one fairly quick. So reasonably speaking, it actually will look more like that, but that's not as much of a problem. Again, you don't want any weird Y phasing oscillations. It just gives you a little more time for it to damp out. On this one, I'm gonna slightly, before they do show this correctly, this is gonna dephase that one and remove the effect. So it's nice and smooth. I avoid any of the oscillations right at the beginning. As I change. So, but this one, you just give it time to naturally damp out because I don't want to reverse it because I don't want to change my space. So this one gives you a slightly more realistic pulse. And realize this is still set, so that and that. So there is a little bit, you don't sample right at the edge, just so you avoid some of the overshoot that gives phenomena ringing. So that's for the two coming down. And that's what you've done so far, just slightly more realistic. Right? Here we've got our echo area that's going on. That's on. This is our measurement along 3. All right, so you can see I'm doing my sampling. I've got my readout area. Now, realistically, I need to kind of turn this thing off too. Okay? So what we want to do is we're going to take, notice I don't give it any amount of impulse or anything. Right? So what would the advantage of selecting that slice be? Because that's all the Z does, right? It just selects that slice.
Could it ramp up the more frequency of whatever's oscillating to
Why would that help?
the down quicker? So it'll come to equilibrium faster.
It's exactly what you're doing, right? Remember, it's going to naturally decay on its own. They don't really move perfectly straight in lines here. There is some natural decay. We try to read it out in a quick enough time period that you're not going to really worry about those type of effects. But if I ramp everybody up, it's going to naturally cause them to decay, particularly that slice, a little bit faster. And so I just kind of accelerate them. It's kind of like if you get to the end of a movie and like, you know how there's the whole credit scene, but then there's the really fun after shots in some movies. Do you sit there and watch the credits or do you hit fast forward? Yeah, fast forward. Right? Remember, time matters to us, the doctor, the equipment, everything else. So this is the fast forward button to bring it back because it's got to be back here. Otherwise, I'm here when I start the next sequence, right? Which is going to mess things up. So bringing it back as quick as I can, hitting a really strong size select, speeds everything up, decays it, and then I can start my recovery and just start again.
I have a quick question.
Sure.
You mentioned that if we don't go back to the original case base, it'll mess up our next measurement.
Yeah, because you're starting here or some decayed version, right?
Makes sense. Is there any, I guess, merit to having a more complicated algorithm to save some time and just start there and move back?
So, yes, there can be, right? The question is, do you know exactly how much it's decayed?
That's true.
The neat thing about this one, you don't need to know where you are because it's pulling everything to the origin. So if you do it too long, guess what happens? It just stays at the origin better, right? If it was a little off and you were here, then all your errors build up. So could you save time? Yes. Could you get more noise or a mismeasurement? Yes. Now, does that mean it doesn't matter? No, it might actually be worth it to me to be able to do that type of a system, right? I mean, you know, maybe to get to here and then to do another 180 pulse and read them out and do a butterfly read or something, right? There are a lot of different advanced reads that are on. Yeah, they do that all the time. Okay, so those are great questions. And this is, remember that time is money on this type of equipment. These things are really, you know, tens of millions of dollars. The more people you can go through, the lower the cost, which means the more economic it is for those people getting an MRI scan. It also, people have problems, you know, it's scary for most people in those tubes. They're scary, they're loud, the magnets clicking to do all this. So, all right. Slightly more advanced scheme, the one we did 2 ago now. All right, because we just showed one where it just went down and went over. So now we're going up, instead of doing it 1, 2, flip, and done, we're going up. This, again, is going to be that whole, in essence, 180 flip. They show it kind of going a little curved path, because in reality it is a slightly curved path. But it's also really hard to read, particularly with the dashed lines on top of this if they don't show it a little bit more. But don't be freaked out by the arc. Right? It's not trying to say this is drastically different. This really is 2 slides ago with the DRAM. So again, RF pulse, it's got to be synced. Whenever you see the RF, you should see Z. Right? You can see Z without RF, but not the other way around. I select my slice, head to toe range. And this, they're both activating, so I'm going to move diagonally. Again, this one is lower and slower because we usually do some correction on the edge. This one, we try to do it fast and let it down. So the combination of this is moving X, moving Y. And in this case, X is always positive. That's why they don't show it bidirectional. Y could be either direction because I could go up or down. Since I'm about to do a flip, I'm only going to move to the right in X. But I could go up, I could go down. It depends where do I want to do the readout. If I'm doing the readout on the bottom, I go up. If I'm going to do the readout on the top, I go down. So that's what's determining this location. The further up, the further up, the further down, the further down. Good? All right, I'm doing this during that FID. I have to give it's mostly died away. This is the ideal time to give the 180 kick. I have to select Z's so that I don't excite the other layers and cause noise. And now I'm getting ready for my echo. So I want to read the echo out. So I have to apply my Lamore frequency perturbation in the X direction. And I read out. All right, so this encodes your X dimension. This reads it out. I get all the signals. I can now get all the frequency components, which is spatially correlated now. And then I need to clear this out, right? And they don't actually on this one show a decay, right? They do give you these. What are these? Bunch of time passes. So I can let a large amount of time pass. Why might I be willing to accept a lot of time passing for this? Yeah, for things to decay out. I have a long TR anyway. So if I'm going to have a long TR, then there's no reason to speed it up because I have to go slow. Not just to get these to speed a little quicker and get down to 0, but I need the whole thing to disappear, not just its echo. Right? So I might just be waiting anyway, so who cares? Why If I have to wait, I have to wait. Yeah, I could, if it's one where I could get shorter, if I'm determining between the 2 and the 6 seconds, then it might make sense during that gap to try to accelerate. What am I trying to decay? Right? And then I'm free to go again. Once TR happens, I am free to go again.
I have 2 questions.
Sure.
Number one, when the Z gradient is active for the 180 tick, is there a reason that we don't go to negative Z gradient to balance it out or whatever like we do first tick?
Yeah, that is a good question. So for this one, we're really concerned that all of these here, this is the kind of our precision kick that gets everybody aligned. Right? This one, I'm literally upending the box. Right?
Less worried about it.
Yes. Plus, I've got both sides are affecting. Right, so this may seem weird, but if I did it on this side, I'd have to do it on that side.
Oh, I see. So it's kind of like it's upside down.
Uh-huh. Because you are literally flipping it on this. Right? And so there is a little bit of automatic cancel out that's happening between the 2 sides. So it's not as bad. This one is literally one-sided because you don't have the other side because you haven't started the pulse yet. Right? So this one, as much as you want that to be perfect, it's not going to be perfect on there. So now you have to kind of fix both the one-sided nature as well as whatever effects go on. On this one, since it is 2-sided, it's a little more balanced. And so I can take advantage of that and time is money.
Okay, so question number 2 is going to be on the curve path for number 3. So number 3 is from the 180 kick, so that's why we do the case base. So is there a reason why that's curved? Could that just be so it's not?
So it's readable.
Okay, great.
Right? It's never going to be perfectly straight. It is nowhere near that bad. Right? You know, but think of it, they can't go down this way because then it'll overlap here and it'll be hard to read. So they had to go up to this side. You know, they could have done a smaller one, but they'd have to move the 2 over. You know, it really, they just over exaggerated it just to make it look, you know, pretty. They're much more attention to detail when they're straight lines, from my experience, than with the curve. Although it is true, there is no such thing as a perfectly straight. As you go through here, there is a wobble that happens near here. It's kind of more like S segments. They're not really strongly perturbed, but it is more of an S segment. Okay. So this would be an example of a polar sequence that's going in. How do I read the whole sequence to it? All right, so remember there are times we're going to do polar, like central slice theorem. So if I want to do kind of the equivalent of a CT reconstruction, that's in essence what we're doing with sinograms and everything else. The one key thing that kind of looks a little wonky, if you think about it, when you're doing echoes. When you're not doing echoes, it's pretty straightforward. You move opposite direction and then read out. And when you're doing an echo, you just have to remember, you have to move to the end, echo, and then read out. That really is the whole thing this graph is trying to emphasize. But notice how complicated the whole system is in order to achieve that fairly simple one. And again, the pulses are fairly complicated, but I'd be willing to bet at this point, all of you could help me to explain this graph. So, help me explain this graph. Right here, what's going on? So where's that? It's actually the pick of that particular origin system.
Right.
Remember, there's slices, so they're stacked. Yeah, so you're picking which origin are you about to fill the polar in on. All right.
Yeah.
What's going on here?
So that is
Select stepping up the X and Y axis.
Yeah.
So why are both of these fuzzed? I thought we didn't do that.
Well, we're moving at an angle, so we need both.
Yeah, and I'm no longer making rectangles, am I? I'm not reading squares with straight lines. I'm getting a circular read pattern, not a square read pattern. All the other ones were square read patterns. The further out you went, you still took a whole line. Okay? So these ones have to be the same because it's that I want a uniform radial motion that's on. So they have to be the same. We try to overlap it with the fit area. What's happening here?
Your 180 degrees.
Yeah, that's the flip the whole box, right? Your 180 kick. And I have to activate the Z for what? Slice selection. Why do I care?
Only getting the Z slice, not X.
Right. So and because I don't get other Z slices,
Other Z slice, that's
right? Because the other Z slices will cause noise interference. What's going on here?
So you're moving along your readout line, and so those would have to be the exact same settings they were before.
Exactly. It has to be that same ratio. Right? So notice they are at the same heights. And it's going to be exactly correlated too. It's not one up versus one down. If I'm on the up, I went to here. When I come down here, I just got to do it twice as long. Right? So they should have measured on this like that and that. So this is identical to that. So it's the echo around it. And then I have to keep reading so I get both sides. Right? And you're maintaining it because that's, and that is your sampling period. So you can see my ADC on. And then I'm up here, so I've got to let it decay or potentially hit it with a Z thing to speed it up, if that will be beneficial to me. And I'll walk through different patterns of the XY gradients to basically give you different slices as I'm reading through them. Okay, good? Yay. I think we're getting pretty close to the end. Okay. So now we're going to take a look at some diffusion weighting, right? Images. So again, when you're looking at these, this is kind of your whole walkthrough on it. It'll look very similar to what we've got. So each of these ones, it's going to again depend on what you're doing for each one, what matters to you for that. One of the key things you'll note on this is I now have to counterbalance your weights. This is really the big difference that you're doing with that diffusion weighted. Again, because now I want to make sure that it's nicely balanced. The other one I say, that's good enough, right? It's flipped, it'll be basically okay. Because I wasn't too concerned about the effects, what that was. When I get to the diffusion weighted ones, I do care. That matters a lot. So since I want to do the correction on one side, I have to do the correction on the other for its symmetry effects. So this is one really matters. That's actually the big difference on this, right? So you'll notice I do distinctly show this one. That ends right at the peak of where my FID is readout because I'm fixing that. So that's going to cause my resonance pulse to come in. Kick, right? Fix, boom. Here is my start of my FID decay. And so now I'm going to do my walk. 1, 2, 3. 1, 2, 3. And while 3 is going on at the end, I'm going to do my clean up for what's about to happen. And my preset that's on. So I'm doing Q3. I'm getting it ready for the flip I'm about to carry out. I carry that out. I symmetrically fix. I'm now clean. So I've done a nice clean flip. I've got a good signal, right? And then everything comes back together for my echo, X encoding, and readout. Yeah. All right. Really, the whole difference between this and the previous one is going to be here. All right. And to be very, very careful, we're doing one at a time. That's pretty much the whole thing.
So what benefit does being careful give us?
So if I'm measuring something, so not all signals are equally strong. Right? So remember T2 star is relatively speaking a stronger signal than T2 is. Not because T2 is any worse, but because I basically have to use it on echo, because T2 star is what you'll naturally measure out. You can't measure T2 without the echo. So since it's not directly measurable, it happens so much later that that signal has had more time to decay. That means your signal to noise ratio is smaller. Right? So now you want to make sure at every step you don't induce any more noise. So you have to be very, very careful at each step just not to do it. If you have a giant signal, you don't really worry about your signal to noise ratio. Right? But if you've got a weak signal, now you do. So as I go into more sensitive small signals, I care more about getting the signal teased out accurately. Good? So these are great questions. Right? Now again, remember, the key thing in all of these is these different ones are just perturbing the Lamore frequency. So that was the equation we did on the very first day. Right? So that's why, like on the homework, she'll calculate the Lamore frequency. It's really a pretty trivial calculation, but everything is about perturbing that because it's those frequencies that you're reading out of the case space. That might even be the end. Yes, it is. So that's basically it. Once I read all these things in, I filled in case space. So how do I do a reconstruction? Yeah, right? It just takes a Fourier transform, because IFFT is basically the same thing, it's just a weighted version. Right? So it's basically a Fourier transform and you get your image. Now I can do a 2D one, basically do one per slice, and you're done. Right? So this is also why we typically do resolutions like 512 by 512, things like that, because FFT is always more efficient than PowerShell 2. So that's why our pixel ones are always going to be PowerShell 2, like 512 right to the 9. So the next step up would be 2 to the 10, so you'd be over 1,000. Usually that's going to be so much slower. Right, because if you do one direction, you do the other. So now your patient has to sit there 4 times as long. So if a typical MRI thing is like 30, maybe 40 minutes, if you were doing it, to double the resolution, that poor person's sitting there for 2 hours basically. Right, that's a little bit beyond. So it's really kind of more of a time constraint that limits our resolution. And that's why we want to limit where we're going to and basically strengthen it. If we can use a field to fix something and speed things up, we're going to do it because we just faster is better. All right, any questions on these?
I have one
Sure.
general question. So a lot of the timing constraints of MRI are, to my knowledge, based on the Lamore frequency. So if the Lamore frequency goes up, everything's faster. So does a stronger...
And the Lamore frequency increases directly with B0.
Right, so is that another...
And B0 is your main magnetic field. And in the 1980s, this was typically, say, half to 1 Tesla, and now it's up to 10 to 12 Tesla.
Okay, so is that also just making CT time shorter, MRI time shorter?
Which means you could get better resolutions. Because the resolutions were nowhere near as good back then as they are now. Right? And they're taking about the same time because that's the limit of what a patient can sit through. If nothing else, the bladder filling. Right? So essentially at that point, the faster or the bigger we make the field, the faster we can take the measurements, the higher resolution we can give to doctors.
So I have another question.
Sure.
So again, since it's taking a long time, do we have to do like breathing, like stuff to make sure it's all lined up correctly?
Yeah, so this is where you do have to be a little bit careful on these type of things. So you usually try to get everybody kind of relaxed and sleeping because that slows down heart and breathing rate if they can be calm. If not, you would have to do some amount of adjustment. We typically do not. Main reason being this adds one more level of panic on most people. We're shoving you in a big metal tube, and now we're giving you a breathing system that's gating you, and we're hooking you up to the wires for them, but those wires, now we have to use non-ferromagnetic wires, so it can be used in there, and then the electrical signal can still cause perturbation that's in there, so it becomes kind of an uglier thing. We can do some by infrared cameras. So if you've seen the motion laboratory on the first floor of the brick, you can see some of those infrared cameras they do to track motion of people. We will sometimes stick cameras like that around patients being imaged, depending on what system it's in. For instance, with our proton ones, we actually sometimes use those exact cameras. And we can monitor your chest motion. And both your heartbeat and your breathing is readable on your chest. Your heartbeat will make about 0.5 millimeter difference in your chest motion. It's really small. But those cameras can read down to about 1/10 of a millimeter, so it's good enough. So we can do stuff like that where you can do breathing data where you're not touched. But if it's a long thin tube, so we're doing a narrow bore to get a good image for like a whole body scan or something of that sort, it's all gone again. Right. So we don't have a lot of choice. Since we're going to read it out over a couple seconds, we hope that it averages. There are areas of your body where it averages better versus worse. Right. So one thing you can do is actually take multiple measurements for the same area and average them. And that will average out some of the motion that's in there. You can do correction, and we'll see the further on we go, people will come up with better and better methods to estimate them. If you can do that, and then you have a 4D CT scan available to you, then you can correct the motion using a fluid mapping. And do them. And that is one of the research areas that I'm working on, is how to do these kind of samplings to re-put it back from 4D into a 3D. So it is an area of interest. It is not majorly done out there just because it's hard. So the best thing you can do at the moment is average. Great questions. Any others? Awesome. Well, we are within 15 seconds of our time. So I'm calling this good. Next time. So I have been told by Jeff we should be able to do MRI measurements. So theoretically next Tuesday we'll meet at his lab in the brick, or no, sorry, not the brick, at the Baylor Science Building. It's not 100% certain. Here's the why. He has to load up the, I forget if he uses liquid nitrogen or liquid helium. He's got to get in his coolant, and then he's got to monitor the system for about a day to make sure it works. If anything shows up wrong, then he has to fix it, which means it won't be ready till Thursday. He believes it will be ready. He's going to aim for it to be ready there. But if a problem happens, research. So what I ask you to do is, an hour or so before you would come to class, check the Canvas site. And on the Canvas site, I will put directions for the day of what we're going to do. There is a very high likelihood it will be over at the BSB, for Dr. Olson's lab. And since we're small, we should be able to do a run through with everybody. Try to avoid large belt buckles, things of that sort, otherwise you're taking them off. You're going to be taking your wallet and stuff out anyway. The space is small. He may or may not want you to do that, but I would strongly suggest you do it. I think you probably will, but just count on it. If you can bring a thumb drive, a new clean thumb drive, one person is all you need. Well, and hopefully each one of you will then get a chance to take an image or copy them over. We do a new clean thumb drive because we don't want a virus on your thing getting on his isolated system, because it's an older operating system of necessity, which means it's got vulnerabilities out the wazoo. So that's why we want it clean. You can take an older one, just wipe it, or a brand new one, either way. He might have some available, I'll ask him. But if not, if somebody could have one available, it's always good practice. And then we'll have each of you take an image, and that's going to be just like with the ultrasound you're reporting. It did take a while. I did get finally the ultrasounds given to me. I'll upload those tonight. So, any other questions?
Is there anything you recommend for us to prepare, either content or anything before we take our residents?
Not really. I mean, you're welcome to review all this stuff, but you'll be talking on kind of some of the practical things of setting up. A lot of stuff is automated on those systems. That's kind of how it's calculated. But think about each one of these and give them some good questions, right? So just kind of show them that engineers know stuff. I know, food. And we can test them and see what we can get done on his for the contrast. Usually it's a very small, he has some MRI phantoms that he uses to calibrate. So that'll be the basic imaging one we'll do. We might actually try to take one of the ones that we did the ultrasound. We're gonna see if those ones can give a response. So we might try to grab one of those too, because it'd be nice to have both an ultrasound and MRI, and then near infrared spectroscopy. All right, well, I will see you all then. Hopefully it will be over there.